All right, so we're talking about functions of two variables, and today we want to talk a little bit about limits and continuity. And so I'm going to give you a somewhat informal definition for the limit of a function at a point, but it's exactly what you think it should be. So we say that the limit as xy goes to the point AB of f of xy equals L. L here is a real number. We say that's the case if the function f of xy, our z, the z values, get closer and closer to the z value L as xy gets closer and closer to the point A comma B. So xy is closing in on AB, the z value f of xy is closing in on the z value L. So if you're curious how to say this precisely, right, I said this was somewhat informal. What does closer and closer even mean? You'll have to wait until you take Introduction to Analysis. That's where we learn those kinds of things. For now, though, I want to remind you that for functions of one variable, we saw back in Calc 1 that the limit as x goes to a of f of x is L if and only if two different limits hold. And so one was the limit as x goes to a from the right of f of x, that better be L. And the limit as x goes to a, I said from the right, I meant from the left. Now from the right of f of x, better be L as well. And so we talked in Calc 1 how you can approach A from the left side or from the right side. There's two different directions you can approach A, and it shouldn't matter which direction you pick, right? It should be the same. And so back in Calc 1, life was easy because there were only, let's write this out, there were only two paths to get to A, from the left or from the right. So what about functions of two variables? Well, let's pick our point. I don't know, let's pick an AB. You can view all of this happening in the xy plane in 3 space if you want. I'm just going to draw it right here. This is my point AB. I'll actually erase that. And now I want to think about some different paths with you. So one way to get to AB is to take that path right there. Another way to get to AB is to spiral in nice and slow and take that path. Another way to get to AB is to do something like that, right? And so all of a sudden you get this horrible feeling, and that horrible feeling is true. There are infinitely many paths to check, right? Yikes. There's lots and lots and lots of ways to go to A. And so let me make a couple of remarks here. So first off, for functions of two variables, the limit at a point exists if and only if the limit along all possible paths exists, and all of those paths, the limits agree. So it shouldn't matter which path you take to get to this point, you're going to get the same limit. And in that case, if they all agree, then the limit at the point actually exists, and of course it is the same thing that all the other limits were. Now, here's the big takeaway for us. If you can find a path C1 where the function goes to one z value L1 along the path C1 and a different z value L2 along the path C2, then in that case, you know that the limit as xy goes to AB of f of xy, in this case, the limit does not exist. All right, so I thought it would be best to illustrate all of this with an example. And so let us look at this function, z equals x squared minus y squared over x squared plus y squared. Excuse me, getting a drink. All right, so we want to take the limit as xy goes to 0. Actually, you can sort of tell this is a rational function. The only place it's going to have problems is at 0. So we're looking at the right place. And so let's just think about what happens as we go along the x-axis. If you want to sketch the xy plane. Yes, we're viewing this in 3 space in general, but for now I'm just going to plot this point 0, 0. I'll plot it in orange, so we're going to plot that. And there's sort of 2 clear paths to get to 0. You can go along the x-axis, and you can go along the y-axis as well. And so let's study those paths. Another path that's nice to check is along the line y equals x. Those typically, one of those 3 paths typically does it. So let's just make some points here, and let's say, look, let's go along the x-axis. Now, if you're on the x-axis, tell me about y. You know y is 0. So along the x-axis, the limit as xy goes to 0, 0 of f of xy, this becomes the limit as, well, y is 0, so now it's just x going to 0, because if we're on the x-axis, y is 0. This is the limit as x goes to 0, and now we can plug y equals 0 into our expression, and so we get, this is just f of x comma 0, which is the limit as x goes to 0 of what? X squared over x squared, and that's just 1. Does that make sense? And notice that when I say x goes to 0 here, that actually is incorporating both the left and the right hand limit here. I'm coming in on the path left and right. Both of those are going to 1. So I actually did do 2 paths in 1. That's perfectly fine. But by coming in on the x-axis, I'm actually fixing y equals 0. Whenever you come up with a line through your point and you study the limit as the particle moves or as your point moves along that line, you're actually doing 2 limits in 1. That's perfectly fine. You can, if you need to, you could restrict to, okay, x goes to 0 from the right if you wanted to, if that would somehow be helpful. But most of the time, just picking a specific path is good enough. So now let's go to 0 along the y-axis. So now, when we do that, we know that x is always 0. And so the limit here, let's just copy this. This limit, we're going to have to erase that word. It got captured. This limit is just the limit as, well, now it's y goes to 0, because x is 0, of f of 0y, which is the limit as y goes to 0 of minus y squared over y squared, which is negative 1. And at that point right there, you know that this limit, the limit as xy goes to 0, 0 of the original function, I won't write it out again, this limit does not exist, because on one path you went to 1, and on another path you went to negative 1. Let's switch the screen to Mathematica and check this out. So I said Mathematica, but I realized I could also graph this, whoa, on GeoGebra. This is my desk. There we go. And so I can zoom in, and you can see this is the x-axis running horizontal like this. The green one is the y-axis, and you can see if you go along the x-axis, you stay at height at height 1. But if you go along the y-axis, then you're down here at minus 1. And so there's this sort of pinch happening right there at the origin. And so that, whoa, sorry, this is a little seasick, but that is what is going on here. So this is the graph of the surface. Maybe we'll switch to Mathematica as well and see if it looks any different. Here is Mathematica's version as well. Pretty much the same graph. You can sort of see that same pinch happening right there. So along the x-axis, we're going to 1. Along the y-axis, we're going to minus 1. And so this function has no limit at 0 because it's different along those 2 paths.